So in Desmos, if you click on this little gear thing here, nope, not the gear thing. If you click on the plus symbol, yes, you can make a table. Oh, you might want to, why? I'm mirrored. Why isn't it? Give me 1 second here. Sorry. I thought I was duplicating, not extending. Okay. Now you should be able to see things that I can also see. And let's minimize this for a minute. Oh my God. Maybe someday ever. There we go. Cool, cool, cool. So let me close this again. So you can make a table by clicking the little plus symbol here and then clicking on table. And then you can just enter the data by hand. So I'm just going to type in these temperatures and chirping rates. So I've got 50 and 20. It's probably easier just to go down the left side before I go across. So 50, enter, 55. Oh, these are easy. 60. It's probably going to start guessing that. Yep, it's going to start guessing if there's a pattern. Cool. Right on. And then the tripping rates are 20, and then 46, and then 79, and then 91, and then 113, 140, 73, 198, 211. And you can't see them at all because we're zoomed too far in. So we're going to zoom out. What, we got 50, so 50. So there we see some of the data points. Cool. Right on. So how do we draw the best fit line? Excellent question. So one thing you totally could do is actually just plot the points and then draw a decent-ish looking line. But really, there's a very technical definition of what the best fit line is. I'm trying to remind myself how you're supposed to do it in Desmos. I know I have a video of how you do it. I believe the way this is going to work, let's see if it works here. I think you write something like, so you're going to use those two variables, y sub 1 and x sub 1. And instead of saying y sub 1 equals mx plus b, you're going to say y sub 1, not capital Y. You have to use the right capitalization here, lowercase y, underscore 1 to get the sub there, right arrow to get out of the subscript. And then you draw this little tilde symbol to give you the approximate line that's going through. So that's what's going to give you the best fit line, or the best fit power function, or the best fit logarithmic function later on. And then you do your mx1 plus b. And then it gives you the slope, approximately 4.85667, and the y-intercept, approximately negative 220.967. It also tells you, this R value here tells you how good of a fit your line is. The closer to 1, the better the fit. The closer to 0, the worse the fit. I should say the closer to plus or minus 1, the better the fit. The closer to 0, the worse the fit. Yeah, that's kind of it. Right, so then looking back at the question says, what does this question say? Oh my gosh, I lost my place. Sorry, 1 second. The question says something to the effect of, find and make a scatter plot. Cool. You could probably even like print this out if you really didn't want to draw things, but it's probably good to draw them. Find and graph the regression line, did it. And then use the linear model to estimate the tripping rate at 100 degrees Fahrenheit. So then you would take your equation, y equal to 4.85667 times x plus negative 220.967, and plug in 100 for x and calculate y. Or you could do it the lazy way and go to your table here and plug in. I'm gonna pick a different number just so I don't give you the answer. I thought you can plug in 110, and okay, can you plug in 110? Maybe not. So I guess what I would do then instead, if I really didn't want to like write it out, is I would just graph the line, y equals 4.86577, sorry, 5667, x plus, sorry, minus 220.967. And then I could go ahead and turn this off. I mean, I could probably, I could do the smarter thing. I can make a table here by clicking on that, and then you can have a table for it, and then you can just plug in 100 or 110. And there's your value. Cool. Yes.
It'll just set x equals 100, and then it'll.
Oh yeah. Where? So would I do that like just below it? So like.
Set x equals 100, and it'll show you the
Oh yeah, sure, yeah, totally, yeah, of course, yeah. It's just giving you the new line literally, and you find the point of intersection there. That is another smart way of doing it. If you had to do multiple values, the table might be easier, but it's also pretty easy to plot or graph x equals 100, x equals 1,000, whatever you need. Questions about this? Yes, and if so, specifically, if you see a problem where there's that little red graphy symbol, right? You see, let me just show you, I guess, so in case you hadn't seen it. Right, this little red graphy symbol right there, you can kind of see it. Zoom in. There it is, real close, that one there. If you see that symbol, that means it's meant to be done with a graphic calculator and probably would be very challenging to do without a calculator because it requires a lot of actual physical calculation. So then let's look at one more example real quick, just because this is something that's actually going to come up later on as well. Well, I was gonna try and pick a slightly different one, just so that you had a chance to do 26 on your own. Let's look at 25. So looking at 25, let me get my Desmos back up here. So also, nice thing about Desmos is if you want something to stick around, but you don't want to like you don't want to look at it, you can just turn off the graph by unclicking those things, which is cool. I don't really need this stuff anymore, so I'm just delete it all. You can also save graphs for later use, which I have definitely saved graphs. So inputting my data from question. So 25 says species area relation for reptiles. The table shows the number n species, reptiles, amphibians, blah, 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 blah. Use a power function to model n as a function of a. So I'm going to say that n is my y, a is my x, because we want n to be a function of a. And so then making a table here, my x values, which are my a values, are the area. So we have 4 and then 40. There's some interesting islands. Puerto Rico is 3,450. No, this is gonna so this is gonna be kind of a wild looking chart because the values are very, very small and very, very big. So there's all my area values for Saba, Montserrat, Puerto Rico, Jamaica, Hispaniola, and Cuba. And then the corresponding capital N, which is the number of species of reptiles and amphibians inhabiting that island, is 5, and then 9, and then whoop, come on in. 40, I think. Yeah, okay, there's 240, 39, 84, 76. And so we're gonna have to zoom way out, at least on the x-axis, to really get an idea here. I think so. Instead of trying to zoom way out though, because like my y values aren't much bigger than 76, right? I don't want to make my y scale really super big. So a better way to kind of zoom out and still see all the things we want to see is to click on this little gear here, and then change the x-axis settings to be from like, let's go, I don't know, -50 to 45,000. That seems largely big. Okay, cool. But it works. It definitely shows us all the points that we're talking about. Cool. So let's first look at what would happen if we tried to do a best fit line, even though that's not what the question's asking us for. So we do the same thing. We use whatever the names of the columns are here. If you have multiple columns, they're going to have different names. So like if you did another one, I should have left the previous one up. If I had done this one with the other one still left up, I would have been like x2 and y2. So I'm just going to use those subscripts as appropriate. So I'm still going to do y sub 1. Well, tilde, not equals. And you can really use any letters you want. It's typical to use m times x or a times x. I don't know why a is typical, but it is. So I'm going to use a this time instead of m. So a times x sub 1 plus b. So the very, very small slope, which makes sense, right? Because there's a lot of run for not a lot of rise. We're getting about 45,000 worth of run for about not even 100 worth of rise. So a very small slope, but not a very good fit. I mean, it's not the worst fit I've ever seen, right? The R value is still not super far away from 1, so it's decent-ish. By the way, if R was negative, it would be a negative slope for the graph. But there's a better relationship. There's a better kind of fit we can try by doing a power function. So instead of doing a relationship where we don't know the slope and the intercept, what we're going to do is we're going to try making a power function where we think of, well, a power function means x raised to a power. We don't know what the power is. We also don't know what the coefficient is. So we're going to say that y sub 1 is equal to, but we don't know what it's equal to. So we're going to use the tilde symbol again. And it's going to be, it doesn't really matter what I use for what, b times x sub 1 raised to the power of, pick your letter. I'm going to pick A. That's how it looks. So this is a better fit. Your log, right? Your r squared value here is much, much closer to 1 than our other r squared value was. Right? You can see it right there. So, and also they told us to do it this way, right? They told us that the relationship should be a power relationship. So that's how you do something like that. And then you can see that the equation is going to be y is approximately equal to 3.42798 times x to the 0.298593. You might round that to 0.3, right? You don't have to write all the decimals. I don't think they say specifically, though, how many decimals you should round it to. So, yeah. So then that's your, that'd be your power function model for part A. And then part B question says, the Caribbean island of Dominica has an area of 291 square miles. How many species of reptiles and amphibians would you expect to find on Dominica? So we can do this number of ways. Let's just say x equals 291. And wow, that's really, really close there. And so we would expect between 18 and 19 species of reptiles and amphibians if this relationship is accurate. Cool. So I believe you now have the tools to do problem 26 with relative straightforwardness. But definitely Desmos is a great way to do it. If you want, later on I can show you how to do it using Google Sheets, but I kind of like to do it using Desmos. Cool. I like that. You're very welcome. Yeah. Let me go back to my other way of showing things here. I will also point out, so when we get to talking about log-log relationships and semi-log relationships, I do have a video on Canvas already about kind of how to do that using Desmos or Google Sheets, but I'm also still happy to talk about it in class when we get there. I have plenty of time. Yeah. I mean, I have a few things I want to make sure I talk about, but yeah, I have time for one more question. And again, I'll say generally, I'm going to try not to exactly do the homework problems because you actually are supposed to like turn them in on your own, but I will try to do problems that are very close in concept. And so, yeah, but yes, yes, feel free to ask away. You've been hearing about it. Have you looked at it? Oh, yeah. Sorry, just, oh my gosh, what am I doing here? I'm extending displays. Yes, okay. Keep the changes. Yes, keep the changes. Okay, okay, okay. You don't need to see the book anymore. She said 24 from 1.3. So and today, this is a question. Let's see, what's due today? Just I'm curious. Today section, well, yeah, 1.2 and 1.3 are due today. How do you turn stuff in for this class? Gradescope. Okay, that's not too terrible. Definitely just as an aside, I would recommend using something like Genius Scan to scan your pages to turn them in. It just makes them look nicer. And then you can make them all into one document relatively easy. It's free, it's easy to use. There are lots of scanning apps. That one's fine. There's other ones, but I definitely would recommend using an app, not just taking pictures. Also, when you do that, you can click on the little batch button at the top right. So it's all your pages in one document as opposed to many different documents. Makes your life easier and the person grading your work's life also easier. So please do that for yourself and for whoever is grading your work. They will appreciate it. They'll be like, yes, I don't hate the student for giving me 10 different documents. They just gave me one, which is lovely. Okay, yeah, Genius Scan. I think it's 2 words, not 1 word. That's the one I use. It's pretty great. Oh my God. Okay, sorry. Back in the day, you actually had to like use it like printer to scan a thing. Ugh. All right, let's see. So let's look at 24 here and see what we're looking at. So the question here, and this is a word question, says, in a normal respiratory cycle, the volume of air that moves into and out of the lungs is about 500 milliliters. The reserve and residual volumes of air that remain in the lungs occupy about 2,000 milliliters, and a single respiratory cycle for an average human takes about 4 seconds. Find a model for the total volume of air V of T in the lungs as a function of time. Ooh, interesting. Yeah, what do they want us to do here at all? So, volume of air in lungs. I'm going to change some of the numbers to protect my integrity here, but not too many. So let's write down the following. Let's say in a normal respiratory cycle, let's say that we are talking about cycle of a Olympic rower. We will say that the amount of air, and I should read this carefully here, the amount of air that moves into and out of the lungs is about 800 milliliters. Interesting that they're not, oh, that's one breath, essentially. 800 milliliters of air. And then the reserve and residual volumes, reserve and residual, I feel like that's meant to be the same thing. So reserve and residual, I guess that means, yeah, I guess what's still left. I feel like why are we using two words to mean the same thing here? I don't know, probably for a biological reason that I'm not aware of. A lot of math is ignoring the biology or whatever the kind of context is when you're trying to actually make things work, and then going back and reading it to recontextualize it. So the reserve and residual volumes of air that remain in the lungs occupy, let's say this person's been really, training their whole life for this. Let's say it's 3,000 milliliters. They've got really big lungs or really big reserves. And a single human respiratory cycle, can I spell? Good God, I cannot spell. And a single cycle for someone who is rowing is about, let's say, 3 seconds. Find a model for the total volume air V of T in the lungs as a function of time. Okay, so let's think about this before we try to write down a function. Yeah, interesting. So time zero, I've just finished expelling a breath. So zero, the volume of air in my lungs is going to be how much? I've just finished expelling. Not zero, although it's not a bad answer, but it's not the right answer. 3,000, right? Because the words tell us the reserve and residual occupy 3,000 milliliters. So, right, you can't fully empty your lungs. There's going to be still some stuff in there, otherwise they'd be like collapsed. I mean, I don't know a lot of biology, so don't believe anything I say really, but I'm pretending like I know that. It seems reasonable, right? You can't expel all the air out of your lungs. So at time zero, the volume is 3,000. And then I breathe in, it takes me 3 seconds to fully breathe in. And now I have how much air in my lungs, according to this model. Right, exactly. I've increased the volume by 800, and that is 3 seconds later. And then 3 seconds later, how much volume do I have in my lungs? 3,000. So this looks very much like we're going back and forth between 3,000 and 3,800. Now, I don't want to write this function just as like only considering when time is 0, time is 3, time is 6, time is 9, right? Those aren't the only times that exist, right? As I go from time equals 0 to time equals 3 seconds, the volume is increasing, right? It's going from 3,000 to 3,800 in some sort of continuous way, right? I'm not like just jumping straight from 3,000 to 3,800. I have to kind of get there. Typically for something that is cyclical like this, a trigonometric function is a good function to model a cyclical behavior. Question?
Why did jump to 3,800 in 1 second.
It wasn't one, so those are all numbers that are 3 apart, even if they don't look like it.
Okay.
So that is a 0, a 3, a 6, and a 9, believe it or not. You'll know if I write a 7 because it'll have a little cross mark on it. My 7s look like this. So that's one reason I write them like that. Yes, that is a 9, believe it or not. So we want, so essentially we want to go through one full cycle. Oh yeah, how do we do this? We want the bottom to be 3,000, the top to be 3,800. So if we're thinking about this, we want our trig function to kind of look like this. At time equals 0, we're hitting 3,000, and at time equals 3, we're hitting 3,800. And then at time equals 6, we're back to 3,000. And then at time equals 9, we're back to 3,800. 0 to 6, and another full cycle from 6 to 12. Or I really should say period. Period cycle, kind of same deal. So there's my graph of my trig function that's representing the volume of air in my lungs. I think we can make up a trig function now. And really, you could use either one of the two. You could either use cosine, you could either use sine. It kind of depends on what you feel more comfortable with. I personally would tend to use, if my function is starting off at a peak or a valley, I would use cosine. If my function is starting off in the middle of the peak and the valley, I would use sine, because then I won't have to do a horizontal shift. So, right, I'm thinking of the middle of this as 3,400. And then I'm thinking of my amplitude of my trigonometric function as being how much above and how much below that's going to go. So I've got I think I can put this in here. So I'm thinking that my trig function is going to look something like y. I shouldn't use y, I should use v of t, because v is a function of t. Be good about that, James. So v of t is going to start off, well, what is my amplitude here? How much up and down do I have? 400. So it's going to be 400 times, I said I was going to use cosine. Cosine of something. We'll figure out what something is in a second. And then we need to, so if it was just 400 cosine, it would look like, fine, just use your tools, James. If it was 400 cosine, figure that out. Guys, this is why I hate doing this over here, because I can't see anything. Sorry. So if we graph 400 cosine, well, there's a few problems with it. Whoa, one of them being you can't see anything. What is going on? What is going on? I am very confused. What crazy thing did I just do? Let's try that one more time. Oh, I think I know what's wrong there. Let's just try graphing cosine of x first and see what happens. Okay. Oh, I'm way zoomed. That's the problem. I'm zoomed weirdly. Let's click the home button to refocus. There's our nice looking cosine function. So first and foremost, I'll point out that this cosine function has a peak first, and I want my cosine function to have a valley first. So I'm going to flip it by making it negative cosine. There are other ways to fix this. That's just, I think, the easiest way. But really, you can kind of do it any way you want. So I'm going to make it a negative cosine. I'm going to write that on my paper too. I'm going to make it a negative cosine. So, and then I'm going to multiply by 400. So it's really going to be a negative 400 cosine. Wow, it's really stretched out. Let's zoom. I actually want to do that. I want to make it much taller, but not much wider. So let's change the y to be between, like negative 500 and positive 500. Sorry, I can't quite see if I delete. There we go. That looks right? Negative 500. And then if I tab over, yep, that works. 500. Cool. So it looks pretty good, right? I'm going down to negative 400, up to positive 400, but then I need to shift the whole thing up so that my peak is really 3,800 and my valley is really 3,000. So I need to add on 3,400. So I add on 3,400, I should have changed my y. Sorry, you can't see it. Okay. Let's add 3,400 here. So negative 500 plus 3,400 is negative 2,900. And that's going to be something 4,300. Yeah, cool. There we go. Right on. So there is our nice looking cosine function. It's got a valley right at 3,000. It's got a peak right at 3,800, but my period is definitely not right. Right? I go through one full period, not in 6 seconds, but in 2 pi, which is actually pretty close to 6, right? It's not that far off, but it's far enough off that we have to fix it. So how do we fix that? Well, that's kind of, in my opinion, the most challenging part here. When you're graphing a brighter, sorry. How do I make this? I know there's a way to make this brighter. That's the button. There we go. So to fix the period for y equal to cosine of x, the period is just 2 pi. Blanket statements. Cosine and sine and secant and cosecant. Not tangent and cotangent. Those periods are 1 pi, not 2 pi. But more generally, if you multiply the x by a constant, that's going to shrink the period. So the period's actually going to end up being 2 pi divided by that constant. So what we typically do is say, well, I want to know what constant needs to go there. So I'm going to set my period, which is 2 pi divided by whatever the constant is, equal to 6, because that's what I want the period to be. Right? I want the period to be 6, because it's going to be from 0 to 6 is how long it takes to go through one full cycle or period of the cosine function. So not 3. It's gonna be something actually kind of funky. So there's a couple ways to solve this. I probably just multiply both sides by b and say that 2 pi equals 6b, and then divide both sides by 6 to get that 2 pi divided by 6 is equal to b, or simplify that to pi divided by 3. So my b, which is the coefficient of x, is going to be pi over 3. And now let's look back to the graph just to make sure it actually looks right. So this is actually what I think Desmos is great for. Like we can work out our answer here and then graph it on Desmos to see if it looks correct. So going back to Desmos, I'm going to multiply that x by, so notably pi over 3 is a little bit bigger than 1, right? Pi is 3.14, 3 is 3, pi divided by 3 is 3.1. So when I multiply the insides of this function by a number that's a little bit larger than 3, I'm going to get a horizontal, oh my God, words. A horizontal what? I didn't quite hear you. Compression, yeah. And what did you say though? I said shrink, thank you. Sorry, I just wasn't hearing it. Yes, a horizontal compression, a squish, a shrink, whatever you want to call it. We're going to go that way. Whereas if you multiply it on the inside by a number that's less than 1, like 1/2 or 1/3, you get a horizontal stretch, or dilation is the word people use sometimes. So we're expecting this to shrink just a little bit. So we're going to do, let's see, pi. I didn't need the slash, sorry, I don't need the slash there, sorry. Pi over 3. And yeah, it shrank just a little bit. And if we look here, our peak is at 3, which we wanted. Our valley is at 6, which we wanted. So that looks like the function that would give us a model for breathing, so that at the beginning of our breath, we have 3,000 milliliters of air in our lungs. And 3 seconds later, we have 3,800 milliliters. And 3 seconds later, we have 3,000, and back and forth and back and forth and back and forth forever, ever and ever, till we die. Yeah. So, but I did make one mistake in my answer here. Not a big deal, but it's a big enough deal that I should correct it. That shouldn't be an x, that should be a t. Because it's volume is a function of time. That should be negative 400 cosine of pi over 3 times e, not x. And technically, we kind of just arbitrarily chose, or I arbitrarily chose, that we were starting at a point of exhalation. But really, you could have chosen to start at any point in the cycle. So it would have been just as fine. You could have literally picked any trig function here if you were. You could have done negative 400 sine, negative 400 cosine, positive 400 sine, positive 400 cosine, all those are going to do is just shift your graph. In fact, let's take a look. I think it's kind of fun to see too. So if you change this to a positive 400 cosine, it's still modeling that breathing. It's just now you're thinking of starting at time equals 0, having fully inhaled. Or if you did it with cosine instead of sine, then it looks like you're starting the process mid-breath, right? You're in between inhalation and exhalation. Here we are inhaling because we are increasing. Or if you want to do it as negative 400 sine, then you're starting mid-breath, but you're exhaling, right? So you're halfway through an exhalation there. If you really want to get fancy, you could then you could start shifting things here. If I wanted to shift it 3, no, let's say not 3, 1.5 to the right, this isn't going to do it. Is it going to do it? No, no, I did. Yeah, because I thought ahead. Sorry. No, it did. It shifted it exactly how I wanted it to. I was just thinking I was getting, nope, it did not. Almost. Oh yeah, right. Yeah. So the problem here is what I really need is this. Good. I was like, I feel like that's wrong. You need a parentheses around that minus x minus 1.5. And now it's actually correct. So if you want to do a horizontal shift along with a horizontal dilation, stretch or compression, you have to do the shift first inside of parentheses and then the dilation outside of that, but still inside the function. Cool. Good question. Yeah, I like that one. Yeah. Because from least amount of air to greatest amount of air in our lungs, what's the difference? No, it's not 400. What is the difference? So our problem was, right, it was 800. So, but the thing is, for a trigonometric function, your amplitude has to be essentially half the amount of the range. So the range here has a distance of 800. And I always think of this middle line here. Right. The middle line is y equals 3400, and the amplitude is how much above and how much below we go. So we go 400 above, 400 below. So that's why we need a coefficient of 400 there. Yeah. Sorry, so what was the question again? I was saying you could have used any of them, was what I was really saying. So it doesn't actually matter which one you use. It just depends on how you want to envision starting. Are you starting exhaled? You starting fully inhaled? You starting halfway through your exhalation, halfway through your inhalation? Really, you could do it something weird and change it completely. I think to me, the most natural starting place is either as you're beginning to exhale or beginning to inhale. That seems like a reasonable, natural starting place for this kind of problem, but really any answer would be correct. Yeah.
Does the line that goes through the function have a name?
The y equals 3400 there. I call it the middle line, but not really. No, it's the midline. I don't know. Yeah, it does not have a name. I usually will, if I'm drawing a trig function though, I will almost always draw that middle line as a dashed line because it's a really good guide for where your important points are. Your important points are either on that line or at the peak or at the middle or at the bottom, at the valley. And it's always just, I always think about when I'm graphing like a sine function, the 5 important points of the sine or cosine function. Sine starts middle, top, middle, bottom, middle. Cosine, on the other hand, typically, if we're starting at the usual, I guess if I didn't shift it, sorry. Cosine typically starts top, middle, bottom, middle, top. So that's how I think about graphing sine and cosine. Is I draw this nice middle line, and then if it's cosine, I start an amplitude's worth above the middle y value, and then I go to the middle, and then to the bottom, and then to the middle, and then to the top. Whereas with sine, it's different. I start at the middle, and then go top, and then go middle, and then go bottom, and then go middle. And each of those points is exactly 1/4 of a period wide. The whole period is how much here? Not quite. Normally it would be 2 pi, but we changed it to be what? We changed it to be 6. Our period is definitely 6 because we're starting at an x value or a t value of 0, and we're ending one full period at a t value of 6. So one whole period is 6 long, and each of these important points on our trigonometric graph occur a quarter of a period later than the next previous one. So from 0 to 1.5, 1.5 is a quarter of 6. From 1.5 to 3, that's another width of 1.5. That's a quarter of 6. Another quarter of 6, another quarter of 6. So whenever I'm graphing a trig function like sine or cosine, I'm always thinking of breaking it up into 4 equal quarters of periods, and then plotting the 5 points that separate those 4 quarters, including the ends.
What do you call it? A single cycle? We don't.
Oh, that's a good question. Let me see here. Well, so they're talking about a single cycle, but then so I would say the final question says, find a model for the total volume of air V of T in the lungs as a function of time, period. So we know that the breathing continues, so we should think of it, right? We don't want to just end the function at, say the domain for the function is t equals 0 to t equals 6. I would say the domain for the function is t equals 0 to t equals when you die. But I mean, or infinity is probably fine. But they're also not asking you to find the domain here, so I wouldn't sweat that so much. But definitely this would be, or whatever our correct answer was, this would be a perfectly fine answer for our model. Okay, can I minimize this? No, I cannot herald it here. All right. Good stuff. I like these questions. Word questions are good. They help us kind of see things that we might not have thought about otherwise. Let's see. Also, and so generally you're welcome to ask questions. I'm happy to look at them. There are a few things I want to make sure I talked about. Yeah. So last time, and so I will just point out briefly, one of the downsides of our class meeting on Tuesdays and Thursdays is from Thursday to Tuesday, you're going to see your professor twice and not me at all. So there's kind of a lot to kind of talk about from what you guys did on Friday and on Monday. A few of the highlights to me that I thought we should cover are briefly talking about domain for a minute, just reminding you of the domain rules we talked about last Thursday. And then what else here? The composition of functions, absolute value stuff. We've talked about shifting a little bit. Oh, inverse functions, exponents. Yeah, okay, cool. So let's briefly review the domain rules. So if I was asked to find the domain of a function, here are the 3 things you should look for. So to find the domain of f of x, look for the following. So the first thing I look for is, does f of x equal some fractional thing where I don't really care what's on the top, but I definitely care what's on the bottom. So if f of x is something over some stuff, we always have to exclude all values of x such that the stuff is equal to 0. So basically you set the stuff in the denominator equal to 0, you find the solutions, then you say, we don't want those, take them out. For example, if f of x was equal to x squared minus 3x minus 4 over x squared minus 1, even though you could simplify this and cancel an x plus 1 on the top and the bottom, you shouldn't do that before you found the domain. Domain is always of the original function, not any simplified function. So if I look at this, I'm going to say, okay, I want to set the denominator equal to 0. And I would factor it. So you get x minus 1 times x plus 1 equal to 0. And then we're going to exclude the solutions. So we're going to exclude from our domain x equal to 1 and x equal to -1. So here the domain would be everything from negative infinity to -1, union everything from -1 to 1, union everything from 1 to infinity, excluding the -1 and excluding the +1. I will point out, because it is worth pointing out, if you were to simplify this expression, it would simplify as x minus 4 times x plus 1 over x minus 1 times x plus 1. And yes, we could cancel the x plus 1s, but that does not change the fact that x equal to -1 still has to be excluded from the domain. Kind of weird. That's the first domain thing I look for. The second domain thing I look for is, does f of x equal the square root of some stuff? Or any even root, actually. So it could be a 4th root, a 6th root. So really it could be any even. If that's the case, then we need to set that stuff to be non-negative, greater than or equal to 0, and then solve that inequality. So for example, if I said something like, find the domain of f of x equal to the square root of x cubed minus 6x squared plus 9x, I would start by setting that stuff in the square root to be greater than or equal to 0. So we're going to set x cubed minus 6x squared plus 9x to be greater than or equal to 0. And then we're almost always going to leave everything on one side of this inequality and just factor as much as we are humanly capable of. That's not true. We're going to factor as much as possible, right? So if you get stuck factoring, make sure you check with someone to make sure you try and factor it as much as we can. So I noticed that first, each of these terms has an x. I'm going to factor out an x. I'm left with x squared minus 6x plus 9. That does factor further. So I am going to factor it further. It factors as x minus 3 times x minus 3, which is x minus 3 squared. And then just like last time when we were dealing with inequalities, we're going to plot all of the zeros on the number line. So 0 goes on the number line for sure, because x equal to 0 makes this whole thing equal to 0. And positive 3 goes on the number line for sure. And then we test points in each of the 1, 2, 3 sections. Before I test points, I should ask, do I want to include 0 and 3 in my solution or not? I should say in my domain or not. I do here, right? Because I want this left side to be greater than or equal to 0. And the value of 3 and the value of 0 are the things that make it equal to 0. So we're definitely going to include those endpoints in this example. Okay, there is a slow way to do this, and there is a faster way to do this. The slow way to do this, which is perfectly fine, and if that's the way that works best for you, then you should do it that way, is to plug in a point in each of the 3 intervals. So pick something like x equal to 4, plug it in, you get a positive number times a positive number squared, the whole thing's positive. Plug in x equal to 1, you get a positive number times a negative number squared is still positive. And then plug in the number less than 0, like -1, -1 times -1 minus 3 squared. -1 minus 3 is negative, but the negative number squared is positive, but then a negative number times a positive number is a negative number, so it is negative over here. That's the slower way to do it. I know it seemed kind of fast and talking fast because there's a lot to talk about. The faster way to do this is to do one of them. So pick 4, plug it in, positive times positive, positive. And then instead of keeping on picking values, you look at the factor that the 0 came from. So x equal to 3 is a 0 of the factor x minus 3 squared. That factor has an even power. When the power is even, the sign stays the same, which it does. Positive stays positive. And the reason that's true is because whether you pick something bigger than 3 or less than 3, the inside is going to change from positive to negative. But when you square something, or when you raise something to an even power, you always get what kind of result? Positive. So it doesn't matter if the insides are positive or negative. The whole thing's going to be positive, so the sign stays the same. On the other hand, x equal to 0 came from the factor x to the first power, which is to an odd power. So when the sign of x changes, that factor is going to change signs. So when you go from, say, picking +1 to -1, well, all of this part still stays positive, but this part changes from being positive to negative, so the sign changes. So when your power of your factor that the 0 came from is odd, the sign changes, either from positive to negative or negative to positive. And then we have to ask ourselves, which parts do we want? Usually it's the positive parts, but if you like we did last time, I think, if you've manipulated your inequality, so it's something less than something else, then you actually want the negative parts. So just be careful. Look and see, oh, this says my stuff is bigger than or equal to 0, so I do want the positive parts. So I want this part, I want this part, I want the endpoints. So I would say that my domain here is everything from bracket 0 to infinity. There are no breaks, so I shouldn't write any breaks. I shouldn't say 0 to 3, union 3 to infinity. Technically, you could if you use brackets on the 3, but it's not incorrect. It's just less correct than it could be. This is the correctest way to write it. Okay, there's one more thing I look for domain, and that is for logarithms. So someone asked me to find the domain of a function. If none of those three things are there, with one small exception later, we say the domain is everything. All real numbers, negative infinity to infinity, fancy R, however you want to write it. So if none of those three things are there, which I know we haven't done the third thing yet, but if none of those three things are there, that's it. Its domain is all real numbers. So the last type of thing is f of x equal to the log with some base. Yes, I can, thank you. Doesn't really matter what the base is of some stuff. So if that's the case, then we're going to set the stuff to be strictly greater than 0. Unlike a square root, which you can take the square root of 0 and get 0, you cannot take a logarithm of 0. It's undefined. And you can't take a log of a negative number. So here, for example, we would say if I had f of x equal to the log base 3 of, what do I want to do here? Sure, fine. Do I really want to do that? Sorry, I'm just thinking about that. That's not good, James. Yeah, that's good. That's good enough. Yeah, we should do that. Fine. The log base 3 of x cubed minus 8. Well, I'm going to set x cubed minus 8 to be greater than 0. This can be slightly dicey, but I think we're pretty safe if we just bring the 8 to the other side. Normally I would say you probably want to factor something like this. This might be an exception. We can say that x cubed needs to be bigger than 8, which means x needs to be bigger than positive 2. And I think if we go back and check, we can see that that's always true. Right? If x is a little bigger than 2, then a number bigger than 2 to the third power will be bigger than 8. The number bigger than 8 minus 8 will always be positive. So that checks out just fine. So our domain here is going to be, you could draw a number line if you wanted to. You don't really need to here, but it's everything on the right side of 2. So our domain here is 2 exclusive to infinity. Just in case you were curious, I will point out you can factor a difference of cubes or a sum of cubes. X cubed minus 8 does actually factor as x minus 2 times x squared plus 2x plus 2 squared. That's sometimes useful to know. I'll point out this part here is always positive. So you're really only getting a sign changing at 2. All right, that's domain in a nutshell. Look for those three things. If you don't see any of them, great. Or I should say, if you don't see any of them, then your domain is all the numbers. All right, what's next on my agenda? Yeah, okay. That's not the right page here. Let me see real quick here. Sorry, I made some notes. I'm just making sure I'm ticking the things off on my notes here. Yeah. Sure. So let's talk about composition for a second here. The composition of functions. There are lots of things you can do with functions, like add them, subtract them, multiply them, and divide them. And although we could sometimes talk about those things, I will just say blanket statement, those 4 things, what I would like to call the arithmetic of functions, adding, subtracting, multiplying, dividing, works how you would like it to work. So for example, I know I say composition, but just for a real quick example, if you have, where'd my dice? Yeah, cool. If f of x is equal to x squared plus 9, and g of x is equal to 2x plus 3, adding those functions works exactly how you would hope it would. you're gonna add all the stuff together. So like f plus g of x is really just f of x plus g of x, which is x squared plus 9 plus 2x plus 3. And then you can simplify if you feel like you want to. It's going to be x squared plus 2x plus 12. That's it. So when you're adding functions, you just add the pieces together and combine like terms if that's possible. If you're dividing functions, same sort of deal. F divided by g of x would be something you'd like to see. X squared plus 9 divided by 2x plus 3. And that's really all you can do. End the story. Interesting. So adding, subtracting, multiplying, dividing functions, you just literally add, subtract, multiply, or divide functions. Questions about this? It would be if that was a 4, but that's a 9. Really, so really, as you've noticed, my penmanship is not excellent. Don't hesitate to ask. Like, because I saw you like, I feel like there's something wrong there. But I'm not sure. If something's adding up wrong because it looks like a number is the wrong number, just ask. It's probably because I've written something terribly. So yeah, that's x squared plus 9, and so 9 plus 3 is definitely 12. So adding, subtracting, multiplying, dividing functions works how you would hope it would. Composition of functions is a little more complicated. So for example, if we had, let's actually use these same two functions. If I wanted to find the composition, f of g of x, you're essentially inputting g into f. So I would often write this as f of whatever g actually is equal to, f of 2x plus 3 in this case. And then instead of writing that f is x squared plus 9, what I'm actually going to do is everywhere I have an x, I'm just going to write in parentheses. So f of x is x squared plus 9. F of some stuff is that stuff squared plus 9. And then whatever is in the parentheses goes in the parentheses. Bless you. So that's how the composition works. The inner function, it's inputted for every instance of x in your outer function. And I do like to use the words inner and outer here, especially later on when we talk about the chain rule. That's definitely how I'll talk about the inner and the outer function is the inner and the outer function. And then sure, you can simplify that if it made sense to. It's going to be 4x squared plus 12x plus 9 plus 9. But really, the simplification is not the point here. The point is that you input the inner one into the outer one. In a similar way, we could find the other composition, the reverse composition, g of f of x. So that's going to be g of x squared plus 9. And g of x says it's equal to 2 times x plus 3. I don't like to say x. I really would encourage you to use the word stuff. I'm going to use a lot. Stuff plus 3. X is just a placeholder. X can be anything. So g of stuff is 2 times your stuff plus 3. And in this case, the stuff is x squared plus 9. And then you can simplify that as well. 2x squared plus 18 plus 3 is 2x squared plus 21. Notice, importantly here, I think, that the reverse composition is not the same, right? G of f of x and f of g of x do not generally equal each other. There are some rare and important exceptions to that, but generally they are not the same. Okay, let's look at one more composition here. All right, I'm trying to go too fast, Jade. Calm down. So let's look at another example. Let's say f of x is equal to, yeah, let's make it not too, you don't need to make it super hard. F of x is x squared minus 4. G of x is equal to the square root of x. And before we do anything, let's talk about the domain. So for f of x, what's the domain? All real numbers, right? We don't have any of the problem functions. There's no fractions, there's no square roots, there's no logarithms. So domain here, everything. How about for g of x? One more time.
Greater than or equal to.
Yeah, thank you. So the domain here is everything. We'll come back to that in a second. So now let's look at first f of g of x. That's going to be f of the square root of x, which is going to be my stuff squared minus 4, which is the square root of x squared minus 4. And that simplifies as just x minus 4. And now the maybe somewhat challenging question, what's the domain of f of g of x? Good question. Is it all real numbers or not? Yeah. So here's the rule that's true for composition of functions. Or actually the rule that's true that I said before. You always have to look at the unsimplified version of the function before you do anything else. And the unsimplified version has the square root of x squared. And if you have a square root of x, x has to be greater than or equal to 0. It can't be negative. So the domain here is that x has to be bigger than or equal to 0, or in other words, everything from 0 inclusive to infinity. Even though it simplifies to something that doesn't look like that would be true, it's still true. Because you have to satisfy the domain. Actually, this is the rule I was really going to say. For a composition of functions, you always have to obey or satisfy the domain of the inner function. And then you also have to look at any other restrictions you might have once you simplify. So here, the inner function g of x has a domain restriction, so we have to obey that. And then the result doesn't have anything else, so we're good to go. Let's look at the other direction. Let's look at g of f of x, which is g of x squared minus 4. I actually like to stop right here and look and say, oh yeah, look, here, my inner function had a restriction. X had to be greater than or equal to 0. Here, my inner function has no restriction. X squared minus 4 has domain, all real numbers. There's no restrictions so far. So then we move on to the next part, which is actually substituting x squared minus 4 into the function f of x. Sorry, into the function g of x. So g of x is the square root of x, so g of stuff is the square root of stuff. I just plug in the stuff. And now I have a function at the end that is probably going to have some domain restrictions because I have a square root of something. I know I need to say that the inside part here is bigger than or equal to 0. Okay, I'll say two things. Yeah, I'll do this. I'm going to do this both ways just so you can see that there is a faster way of doing this. Normally, I would always play it safe for domains where you're solving inequalities, and I would factor as much as possible. So here you could factor the left side as x minus 2 times x plus 2, bigger than or equal to 0. You might recognize that x squared minus 4 is, if you graphed it, had what kind of graph? Yeah, it'd be a parabola, right? This would look something like this. An upward opening parabola, right? So it looks like the part over here and the part over here is when x squared minus 4 would be positive, and the part in between those two x-intercepts would be when it would be negative. And those x-intercepts are negative 2 and positive 2. So it looks like we're probably going to get everything that's not in between negative 2 and positive 2. So like everything out here and everything out here. And we would, if you plugged in a number like 3, positive, positive, plug in 0, negative, positive, plug in. I guess that I should do it the fast way, right? Those are all odd powers, so the sign changes every time. So it changes from positive to negative and negative to positive. But sometimes it's tempting to say, I don't really want to factor that, even though it's not that hard to factor. So I will point out that specifically when you have x squared minus a constant bigger than or equal to 0, you can do this thing where you just say, oh yeah, I'm going to say that x squared is bigger than or equal to 4, and I'm going to take the square root of both sides. Okay, don't let me trick you. I'm going to try and trick you. Don't let me trick you. What's the square root of x squared? Don't let me trick you. There's something more than just x. You're on the right track. So close, you're all so close. Absolute value is the absolute value of x, which I know feels like it's the same thing as plus or minus x, but it's not really. So it is the absolute value of x has to be bigger than or equal to 2, which means either you get x bigger than or equal to 2, because x could be 3 or 4 or pi or 17, and that would work, or x has to be bigger than -2 or smaller than -2. Smaller is the bad word here. I don't like the word smaller, because when I use the word smaller, I usually think in my head closer to 0. And that's not what I mean in this context. So when I say, which I should say, more negative than -2 or less negative than -2. I want to be more negative, right? I want to be further, right? Again, the language here, like you probably thought you were saying the thing that you thought was right. And I was like, well, that's not the thing I'm thinking. So when I say more negative, I mean a bigger negative number, like -3, -4. Going away from 0 is a larger number in absolute value. So I would use absolute value. So a more negative number is going to work like -17 or -28 or -3. It does not really work here, actually. You have to kind of write it as two separate inequalities. There's really no way to do it. If you wrote x bigger than or equal to plus or minus 2, that wouldn't convey what we really want to say. Because you don't want, because if you write this, the problem is you're saying x bigger than or equal to 2 and x bigger than or equal to -2, and that's not what we want. We want x to be less than or equal to -2. Because if you want to be bigger than the number on the number line, you have to be to which side of it? What's bigger than? The right side, and less than is the left side. And I remember by saying less than and left start with L. So the less than side is the left side of a number, the bigger than side is the right side of a number. I know, it's annoying. I wish there was a better way to write it, but there's not. So here our domain would be everything from -infinity to -2 inclusive, union everything from +2 to +infinity. Yeah, well, so kind of, but again, I'm saying if you felt comfortable doing it this way, you could probably skip the number line. But again, my default recommendation would always be to use the number line when you're finding a domain. I think it's the best way to do it. Not just like the safest way. I think it's actually the best way. It works the nicest every time. It's consistent. It always works. So usually if you're trying to find the domain, you want, and you have an inequality, it should be everything on one side, 0 on the other side. Back to the one side as much as possible, put your zeros on there, and then find the thing. Yeah. Sorry, I'm just thinking about one thing here. Fine. Yeah, one more example. Interesting. That's weird. Sorry, there's a little thing that says like talking, not talking. So let's look at one more example because there's one more tiny thing I want to say, which is, yeah, what if we have something like, I'll try and not make it too terrible. Yeah, I want that. Okay, let's say that f of x is equal to the square root of x minus 3 over x plus 4. So we want to solve the inequality x minus 3 divided by x plus 4 is bigger than or equal to 0. Now let me ask you all, what is the only single value of x that makes this rational expression equal to 0? That is the next answer I'm looking for, but not the answer to the question I asked. So what could you plug in for x that would make this whole thing equal to 0? Show me on your fingers. Yes, that many, exactly, 3. Because if you plug in 3, 3 minus 3 divided by 3 plus 4 is 0 divided by 7. And how many times does 7 go into 0? 0 times. So 3 is our only 0, but it's not the only place the sign of this expression can change. Because at -4, we would have, if we graphed it, we'd have a vertical asymptote. So in fact, let me graph it. Graph this thing. Okay, James, you said you're going to graph it. If x is 0, you get -4, so it looks like this. Okay, cool. +1, right? looks vaguely like this. And there's a horizontal asymptote at 1, but I don't really care. Here's the vertical asymptote, x equal to -4. Here's the x-intercept, x equal to +3. And these two places, x equal to +3 and x equal to -4, are the only places where the sign of this function could change from positive to negative or negative to positive. So to be really kind of inclusive of all possibilities on your number line when you're finding the domain of a function, you have to include every place where this side of your inequality could either equal 0 or is undefined. So it's totally correct to include the -4, but the reason we're including the -4 is because it makes that expression undefined. And then we already can see from my graph here what's going to happen. But if we test points, plug a number like 7, 7 minus 3 is positive, 7 plus 4 is positive. And the nice thing is that division and multiplication work the same way, in that if you multiply two positive numbers together, it's positive. If you divide two positive numbers together, it's positive. So a positive number divided by a positive number, still positive. You plug in a number like 0. 0 minus 3 is negative, 0 plus 4 is positive. A negative number divided by a positive number is a negative number. And finally, -5, negative divided by negative is a positive. The word that often comes to mind when I'm doing this is the parity, right? If you have an even number of negative things multiplied or divided together, the result is going to be positive. If you have an odd number of negative things multiplied or divided together, the result is going to be negative. That's what I'm always keeping in mind when I do this. You can write more things down. I don't particularly care to do more writing than I need to do, but some people like to make like a whole, I can't even bring myself to even start doing it. But people like to write out like a whole chart with like the x minus 3 and the x plus 4, and then like the whole function, or at least the whole insides. And then they like have x bigger than 3, and that's positive, and that's positive. So the division is positive. And then, oh my gosh, I don't like doing this at all. X is between -4 and 3, so like 0, so that's negative, that's positive, you divide them, it's negative, and so on. X is less than -4, that's negative, negative, positive. You can do it like that, but you don't need to do all that. I despise doing that. So not that you shouldn't do it if it works for you, right? If it works for you, you should do it that way. I don't like doing that because it's more writing than I need to do. If you can do this and just be like, oh yeah, positive, negative, positive, that's fine. Okay, here's a trick question. Do I want to include the endpoints? Yes, like you said, it's a trick. Yes, on one of them I do. So I want this to be greater than or equal to 0, and we just spent a whole minute or two talking about how which value of x makes it equal to 0. Right. So we definitely want 3. We definitely don't want -4 because -4 makes the whole thing undefined. We never want to include values of x that make the function undefined in our domain. So here the domain would be everything from -infinity to -4 exclusive union 3 inclusive to infinity. Okay, cool. Good there. All right. Yes. Oh, sorry. So I should have reflected here. So I want all this stuff to be greater than or equal to 0. That means I want all this stuff to be positive or 0. So I want all the positive parts. I want the part that makes it 0. I want none of the negative parts. I want all the positive parts. So I want all the numbers less than -4. I don't want any number between -4 and 3. I want all the numbers bigger than or equal to 3. That's how I'm using the positives and negatives there.
What can make the equation?
Right, what can make this expression positive. So when I'm writing the sign here, it's the sign of this expression here. So that's why I'm plugging in a number like 7 and saying, oh, 7 minus 3 is positive. 7 plus 4 is positive, and I know that a positive divided by a positive is positive. Okay, not a long time. All right, so enough about domain. Sure, I'm going to skip the shifting and stuff because although it's important, we kind of talked about it already. I want to jump straight to talking about inverse functions for a minute. So the whole idea with an inverse function is that you are interchanging the role of x and y. So some great examples are f of x equal to x cubed, which looks like this. And if we wanted to find its inverse, the process for finding, so you might know the inverse already. And sometimes they're really easy to find because an inverse should literally undo what the function did. So this function takes an input and cubes it. How would you undo cubing something? You cube root it. So you already sometimes just know what the answer is going to be. You're like, oh yeah, the cube root undoes the cube. If you want to do the process though, the process is step 1, replace your f of x with y. It's kind of a non-step. Step 2, which is the most important step, interchange x and y. Some people do this step last. I like to do it second. Step 3, where you're going to do any of the work, actually is solve for y. So take the cube root of both sides. I'll remind you heavily here, the square root of x squared is the absolute value of x. The cube root of x cubed is regular x. Odd roots undo odd powers perfectly. There is no absolute value BS. Even roots do not. Even roots of even powers have to have an absolute value if you're going to try and simplify them. Because you can't take an even root of an odd number, of a negative number, sorry. So cube root of y cubed is just y. So we get the cube root of x is equal to just y. And then the last step, which is also kind of a non-step, is to rewrite y as f inverse. So write f inverse of x. You should not say f to the negative 1. You should say f inverse of x is the cube root of x. Or if you prefer, f inverse of x is x to the 1/3. Both are fine. And that function looks like, it literally looks like you took that function and reflected it across the line y equals x. That. And literally, the x and y coordinates interchange values. If you have the point 2, 8 here, in your inverse graph, you're going to have the point 8, 2. Every xy coordinate pair interchanges to get the inverse coordinate pair. Yeah, let's look at another thing. So some examples are not too terrible because they're relatively easy to solve. Some of them are really challenging. A very typical kind of example is something like g of x equal to 7x plus 3 over 2x minus 4. Here's a function that's hard to find the inverse of. No, I won't say that yet. Actually, I will. Will I? Won't I? Will I? Won't I? Yeah, I will say here, I'll point out the domain. I'm going to do it kind of the lazy way, is everything except for x equal to 2. It's not the right way to write the answer. It's just that I'm going to write it right now. And just so you all know, if you were to graph this, this function would have a horizontal asymptote. And the horizontal asymptote would be at 7/2. And the way I know that is because this is a rational function and it has the same degree on top and bottom of 1. And when that's the case, you take the limit. I haven't talked about limits yet, we're going to get there. But we take the limit as x goes to infinity, the limit ends up being just a fraction of those leading coefficients as long as the top and bottom have the same degree. So a horizontal asymptote in this case would be y equal to 7/2. And although this isn't always true, it is true in this example that 7/2 is excluded from the range, right? So the range excludes that value. Because the graph, sure, I got 2 minutes. The graph looks that Matt James. The graph looks like this. Y equals 7x plus 3. I do have a point. It's kind of nice to see. I can, yeah. So there's my graph. Go home. And then if you graph the X asymptote. There it is. Never touches the graph. You graph the Y asymptote. The Y asymptote, or the horizontal asymptote, is the word I should actually be saying here. A graph can cross its horizontal asymptotes. That's not the horizontal asymptote. I said it was 7/2. This one doesn't, though. Some graphs do. We'll talk about those later on. This one does not. And that is the only value that is not in the range of this function. It's close to on either side, but never equals it. So there's a point, I promise you, and we're a minute away from seeing it because there's a minute of class left. So let's find the inverse function. It's the same process. We're going to replace g of x with y. We're going to interchange x and y. So there should only ever be one y that's going to turn into one x. But you could have multiple x's turn into multiple y's. So we're going to x equal to 2y plus 3 over 2y, sorry, 7y plus 3 over 2y minus 4. And now your job is to solve for y. But the intermediate step is to make sure you isolate all the y's on one side and all the not y's on the other side. So I'm going to multiply both sides by 2y minus 4. I don't really want to write out this side, but I will. The point of this is that you're going to cancel in the denominator on the right-hand side. You're going to distribute the x on the left-hand side to get 2xy minus 4x equal to just 7x plus 3. And then you're going to collect all of the x's, I feel like I made a mistake here. I did. Yeah, I changed that y. So this is a good example of how it's easy to make a mistake if you're not being really careful and trying to do things really fast. That y accidentally turned into an x and it shouldn't have. That should be a 7y there. And I knew I made a mistake when I said I want to collect all the y's on the same side and I only had one y. I knew I should have had more than one. So then I'm going to collect all the y's on one side. Let's bring them to the left. So 2xy minus 7y. And everything else on the other side. So a positive 4x plus 3. The reason we do this is so that we can factor out a y from the side that has all the y's. So we have y times 2x minus 7, still equal to 4x plus 3. And finally, divide by whatever's multiplying y to solve for y. So you get 4x plus 3 over 2x minus 7. Okay, so our inverse function here is 4x plus 3 over 2x minus 7. And what I want to point out, and this is kind of why I did this example, is the domain of G inverse of x is everything except for 7/2. And the range of G inverse is everything except for 4 divided by 2. And it is not a coincidence that the domain and the range of these two functions have interchanged. Because when you talk about the domain of a function, you're talking about all the things that x is allowed to equal. Well, if you interchange x and y, then you're talking about all the things that y is not allowed to equal. So when you interchange x and y, the domain of the original function becomes the range of the inverse function, and vice versa. The range of the original becomes the domain of the inverse. The reason this is extra useful, in my opinion, is occasionally you might get asked to find the range of a function. And it's really hard, or maybe even impossible, to graph it on your own. You don't have a calculator. Graphically is nice, though. But you can find the range of a function by finding the domain of its inverse. If I hadn't told you that the range of this function was everything except for 7/2, we could have found the inverse function, found that 7/2 wasn't in the domain of the inverse, said, oh, that means that 7/2 isn't in the range of the original. I thought I saw a hand over here. No, okay. All right, I'm out of time. I should stop talking. See you all. I have office hours today at 4:30 down in 2058. And yeah, that's it. See you on Thursday. We'll talk more about exponentials. We'll start talking about exponentials and logs. Probably. Unless something else comes up. It's more important.